who will present flavor physics from a theoretical perspective. Thank you, Gino.
Okay, can you hear me? Yes. So it's a great pleasure to be here. Really grateful to the organizer for inviting me to this beautiful conference and especially to this beautiful country. I mean, it's the first time for me in Brazil, so it was really a pleasure. So I have the difficult task to give you an overview, theoretical view about flavor physics in only 20 minutes, which is almost impossible. Fortunately, there are 3 more talks after me that I'm sure will do a better job. So let's start with the general introduction. Okay, so I mean, why flavor physics? I mean, flavor physics is really one of the biggest challenge that we have in particle physics. Is a challenge that was there even before the standard model was formulated. So why we have 3 copies of fermions with identical charges, but very different masses. Okay, this is a big question. Of course, in the standard model, we know how to describe the masses of elementary particles. We do that via the Yukawa interaction. So there is really an inescapable link between Higgs and flavor. So we cannot do Higgs physics without understanding flavor and vice versa. And the idea is that there has to be some UV theory, okay, can be strings or more complicated gauge interaction, that will determine this coupling between the Higgs and the fermions. And I like to call these couplings, the Yukawa coupling, a nice message from the UV. Because, you see, contrary to the gauge interaction, the Yukawa couplings are numbers, okay, which really are not protected by symmetry, so really are telling us something about the UV completion of the standard model. And what they are telling us is, one message is very clear, that the UV dynamics, so what's there, what determines this interaction, is clearly non-universal among the different fermions. So there is something there in the UV that distinguishes the different fermions, so, which is not our standard gauge interaction. Okay, now we know very well this Yukawa coupling. Actually, we have very precise determination of the CKM matrix, which is nothing but the misalignment between the Yukawa coupling. This was updated here at this conference about the determination of the CKM matrix. But let me remind you that really the fundamental object is the Yukawa coupling, which is it's a combination of eigenvalues and this mixing. And this Yukawa coupling is really peculiar, okay? Because it ranges from an entry which is about 1, which is the top, up to an entry which is 10 to minus 5. So clearly, the message is that there is something there in the UV that not only distinguishes the generation, but is also very peculiar, because really there is this strong hierarchical pattern that it's not expected, we cannot understand it in the standard model. So really, it's a signal of something that goes beyond the standard model. Now, okay, it's a general field theory argument that whatever is there, this is the Yukawa coupling, which are numbers, is the low energy imprint of this non-universal interaction. However, these new dynamics that couple fermions and Higgs will also couple 2 fermions and 2 Higgs, or 2 fermions, Higgs, and photons. It's unavoidable because they are all charged. And then this will show up as possible deviation from the standard model in rare processes like BS mu mu or mu 2 gamma. And the key difference, again, this is general field theory argument, is that while this is adimensional, so somehow is insensitive to the scale, the effect here is sensitive to the scale. Okay? This effect here is scale with the mass, with the scale of new physics. And as you know, we don't see any deviation here, and this is usually expressed in these tight bounds on the effective scale on new physics from flavor evaluating process. But I think this way of presenting a bound is very misleading, because it's based on the fact that we assume the coupling to be 1. And the coupling doesn't need to be 1. See, there are somehow 2 ways to interpret these bounds. Okay, either you really think that new physics badly violates flavor, so if you want, it's an anarchic structure, and then, okay, the coupling can be over the 1, and then you are forced to be this heavy new scale, but then we have problems, because then we don't understand why the Yukawa coupling are hierarchical, and also would have really huge tuning in the Higgs potential, as was already discussed, because this means that there are new scales there, very heavy, that will impact the Higgs. On the other hand, I think the natural way to think of this is that the new physics scale can be as low as UTV, because also new physics couple in a kind of non-universal way with small coupling to the light families, as we see in the Yukawa coupling. So in this way, we can understand the structure of the Yukawa coupling, and we have reducing tuning on the Higgs potential. And let me just show you one example. For instance, We already discussed this math, and one can show that with very simple ansatz on the flavor structure in new physics, you can pass all the bounds, I mean, really all the bounds on new physics with really small tuning on the parameter, and to have all the bounds below 1.5 TB. So new physics can be there at around 1 TB, and to be there requires a non-trivial flavor structure. So this is, for instance, new physics coupled mainly to the third generation. Anyway, if you don't buy that, it's clear that flavor is very important. Either, if you want, if new physics is bad evaluated flavor, you really have access to very high scale, which are not directly accessible, or in this more interesting scenario where new physics has reduced coupling to the light generation, which actually we have a signal of that in the Yukawa, then there's really a key interplay between Higgs, flavor, and electroweak. Okay. So now let's go a bit deeper. So the way to analyze these bounds and one also possible anomalies is to use this math. Okay, this math has already been introduced many times at this conference. It's nothing but encoding all what we think come from heavy dynamics into contact interaction. This is, again, it's a completely general field theory statement. If there is new dynamics out there, it's heavy, will manifest as contact interaction. Now, when we discuss about math, usually many people are scared by the large number of parameters that we have here. And the parameter, if you don't assume anything about flavor, it's huge, 2,500 free parameter at dimension 6. But you see that if I impose a flavor symmetry, I reduce this to 47. So this is telling you that flavor is really the most important property of this math. So we need to understand flavor if we want to discuss this math. And decoding this flavor structure is essential if you want to understand what the nature of new physics. So how we can live in this space with so many parameters. Let me also stress this point. This large number of parameters, these are not fundamental couplings, okay? These are basically observables. So whatever UV theory we have, we can generate a lot of effect. And this is the big number of parameters. So this is things that we can measure. And then, of course, the UV theory will predict this in terms of few parameters. So the idea is to decode new physics doing a lot of observable. Probably we don't have 2,500 observable, but several hundred we have. Okay, that is a virtue. Now, if you want to navigate in this parameter space, it's useful to employ flavor symmetries, which tell us, I mean, for instance, why the Yukawa coupling are what they are, and also they help us to protect flavor rare process. So, for instance, a typical symmetry in flavor is this U2 symmetry, which if you enforce U2 symmetry, you forbid all the entries in the Yukawa coupling except the third generation, which actually is already a good approximation to our standard model Lagrangian. Of course, we have to break it because light quark have masses, but the breaking is small. Okay, also this explains why we have small effect in flavor changing process. And usually, global symmetries are not so nice from a theoretical point of view, but we can, for instance, have that as accidental symmetry from specific construction, like this idea of flavor deconstruction, where we have a gauge symmetry which acts differently on the light generation with respect to the third generation. So there are nice explicit construction where you generate these symmetries as accidental symmetries. Okay, this I think is there is a nice model building avenue which is quite promising these days. Of course, this is not the only option. It could well be that the Yukawa coupling are generated all at very high scale. This is what we call the minimal flavor ansatz, which, for instance, is what was always enforced in supersymmetry Suzy-Gatt theories. And in this case, the important symmetry is U3, because you basically forbid all the Yukawa coupling. Or you can have other construction with U1 symmetries, and then here the UV completion is different. So I think here there was a very nice recent work by Grelio and collaborator who somehow tried to analyze which are all the relevant symmetries which help us to keep TV scale new physics, and there are not too many options. So there is this MFV, which is the biggest symmetry and therefore the smallest breaking. Then there are these U2 symmetries, and then there is other option which are SU2 times U1 symmetries. And again, this is just a classification of symmetries, but they correspond to different UV hypotheses. For instance, here there is a nice work by Arkaniamed and others with a tower of vector-like fermions, which fill in this area here, or this flavor deconstruction which predict U2, or supersymmetry that predict MAV. So you see, it would be nice to identify which is the correct setup. There are not too many options. And how to do that? We need extra information beside the Yukawa coupling. So we have to go there and try to measure deviation from the standard model in this long list of observable. And right now, those with which we have a lot of precision is very limited. So basically, we have high precision only on B sub S and B sub D mixing. So let me now go to see some of the interesting results which have been presented at this conference. So this was somehow the general introduction of why this is interesting, and I pick up some of interesting results. So first, let's look at this famous RD star plane. So here, this is a test of universality, okay, in B2C L nu transition. Here, if there is something related to the third generation that coupled mainly to taus, you will see a deviation from the standard model in this ratio. You see here, there is this long-standing tension with the standard model about more than 3 sigma. Here, the big news at this we can easily explain it in motivated models, okay? The interesting news here is this recent result by Babar, which, well, you know, Babar is very old experiment, but new result, new analysis, which actually is in bad agreement with the old Babar result. I think this will be discussed more maybe in the experimental part. Clearly, here, you see, in this, without the new Babar, everything is consistent. The p-value of the experiment is about 30%. If we put this new result, the p-value goes down to 0.8%. So clearly, here there is an experimental problem. So the tension is far from being settled. I mean, it ranges from 2 to 3 sigma, depending on how you want to treat this result here. Nice thing is that there are other ways to get to solve this tension. For instance, looking at JEP psi here rather than D and D star. Here, there's been some interesting progress. Also here, there is an excess, not highly significant. Both CMS and LCB see an excess. And finally, one can even look at B2U transition, which are closely connected. Here also there is very minor excess by BEL2, but the nice thing is that BEL2 can really improve here in the next few years. It's really an area where BEL2 with the high statistics can settle the issue. Now let me change, and let's go to what I consider probably the most interesting recent result and analysis in the sector of rare process, which are this B2S mu process. As you know, there is a long-standing tension, discrepancy between the observation here and this prediction, okay, which are not universally accepted, but are the most accepted prediction for this rare process. So what is the status? Well, and there are a lot of observable, okay? So we have B2K star mu, B sub S 2 phi, B2K, several channels. There is a coherent pattern emerging that there is a discrepancy between data and theory related to the vector part of the amplitude. So vector part means something of this type, B2S LL, with the 2 leptons in a vector state, okay? Like if they were produced by a photon. Here there is a very nice, interesting, if you want, new physics interpretation, because if there is an anomaly in B2C tau nu, the SU2 counterpart is B2S tau tau, okay? So really just, these are 2 left-handed fields, so if you have C, you also have S, and then if you close the tau loop, you'll generate exactly a correction to the coefficient of this operator, which goes in the right direction of, see, it's a 10% correction, which goes in the right direction to explain the data. However, the big elephant in the room is the fact that there is also QCD, and with a kind of similar topology here, we can have Charber scattering, which will also kind of produce non-perturbative effect can somehow mimic the new physics. And this is difficult to compute because it's non-perturbative. So what we can do? Of course, one can take a very conservative approach, say, well, give up in predicting the vector amplitude. This is certainly an option. It's conservative. You can still do a lot of interesting tests like lepton fellow universality, attended currency evaluation, but you somehow lose somehow the possibly more interesting part, which is this vector amplitude, which is connected to the B2C tau anomaly. Now, what I want to discuss in the next few minutes is that the precision and the richness of the latest B2K star mu data by LSEB, where they really have done a beautiful job doing both an amplitude analysis and a combined bin analysis, allow us to really understand the QCD part. And this, I think, is really interesting. And actually, this analysis we did recently in Zurich, well, Zurich and Mainz, and the outcome of this is that the long distance that we can extract from data reduce the tension with the standard model, but not completely. The tension remains, okay? The significance is smaller, but actually the size also is much more coherent with what we expect, because it's more coherent with what you expect from B2 tau nu. And most important, these things you can extract from data, you have a way to test it, how good it is. So let me show this with some plots. So for instance, you see, this is the B2K star mu mu. This is the pure standard model short distance, no sharp loops. These are the data, so clearly far off. Here, the observable is the process is very rich. You can measure several things, several distributions. For instance, there is this famous S5, which is connected to P5 prime, which is really sensitive to the value of C9, but also to long distance. But there is something else like this S7, which is on the other hand sensitive only to long distance. Now, the standard QCD calculation of the long distance part, if you want the perturbative one, give this result here. Is from this result that you infer this big discrepancy with the data. But you see, yeah, I told you, this is clearly, it's a difficult thing, and relying on perturbation theory is misleading. And what we have done recently is a more data-driven analysis using dispersive approach to extract this long distance from the full spectrum, use information from the JEP psi and the psi prime, which are the dominant rescattering effect. And now you see much better agreement with data. Not yet perfect, but much better. So clearly, now I think there is a general consensus that a significant part of the discrepancy can be due to QCD. The point if it is all QCD or not, and I think now with this approach we can really control the things, so we really have a prediction based on non-perturbative, complete non-perturbative physics. So here, to really fit well the data, we need this extra, if you want, new physics contribution, and we can test if this is really new physics or QCD, because we can extract in several different bins, and they are all consistent, so it's also independent from the helicity, which is very nice. So it's a nice consistency test that things works. And also there are these other observable, which, again, provide a good consistency test. And so the main message here I want to give is that combining more precise differential data, binned and amplitude feed on different modes, because there are many others that we can look, really give a realistic process for a precise standard model test on this interesting vector amplitude. Now, unfortunately, time is short, so let me change channel. Let's discuss S2D nu nu. This was one of the golden modes for flavor physics for a long time. This is, here we don't have problem long distance. It's a beautiful short distance dominated channel, and finally, after several decades, we have a precision measurement, a 20% measurement by NACC2, which actually still have more data to analyze. And this is really a unique probe of many motivated models. Let me illustrate this here in this plot. You see, the way we interpret the result depends on which is your UV model. For instance, you can interpret this assuming that there is a flavor changing coupling of the Z boson. And you can make different hypotheses, for instance, minimal flavor structure or partial compositeness. For instance, in MFV, you see that you can connect it to electroweak and B physics. In this case, K pi nu bar is not very competitive versus BS mu mu, while in this other case, for instance, the K pi nu bar gives the most important constraint. So again, depending on your flavor hypothesis, this result is really unique. Let me say one important thing. In B2S nu nu, we are still far from that level of precision. There is a tantalizing big signal 3 times the model, which is difficult to accommodate in realistic flavor model, but maybe we accommodate it with line physics. And I think I have to skip that. This will be discussed later on by Carla. Let me just spend a few final words on future prospects. You see, before coming here, I was in the Amazon, and I took this picture on a beautiful place in front of Rio Negro. And I think this is a clear indirect signal of the sun, right? Which is what it's like what we want to do in flavor physics. And you see, the information that you get is really beautiful. Of course, always arrive before the direct signal, and also contains more information, because for instance, these clouds here, they don't see yet the light. So you get a lot of information from the indirect signal. And also, indeed, is the beginning of something. And indeed, I think I think in flavor physics, we're really at the beginning of something very interesting, because for the first time in history, I think we are approaching a systematic 10% level of precision in several processes. First, previously, we basically only had B-bar mixing, B-sub-S mixing. Now we start to have it also in B2SLL, B2C, this process with neutrinos. And the most important thing is that we also have a lot of more data to be analyzed. So here I could not discuss anything about the lepton flavor. We'll discuss later on. Look, LSEB and BEL2 have a lot of data, and this will be super interesting. Also, there is a lot of progress on the theory side. Lattice QCD, again, we'll discuss later on. Also, this new analytic method. And just as an illustration, here, maybe just one last plot, because I am 1 minute late. You see, this is, sorry, maybe I should. This is where we are now with the bounds, okay, on several contact interaction, basically around 1 TeV, okay? And this is where we can hope to go. You see, this is the progress we expect with the upgrade of LSEB and BEL2. And of course, finally, the best things, the ultimate flavor factor will be FCCE. So I think there is really a bright future to go from the 1 TeV where we are now to the 10 TeV. So conclusion, I hope really convince you, and I hope you will be convinced that really flavor physics is super interesting. It's really a key if you want to understand what's beyond the standard model. Beyond the standard model, the TeV scale is only possible if new physics has a non-trivial flavor structure, and we are really starting to prove this flavor structure in this interesting 1 TeV regime. And really, we have a lot of new data to be analyzed that will really bring us deeper in this region. So I think the future is really bright. Thank you.
Thank you, Gino, for the nice overview. We have time for Ignacio.
Thank you very much for the beautiful seminar, and I appreciate in particular your concern about the long distance contribution in the case star Mumu. Could you talk a little more about what kind of long distance you include in your study?
Yeah, thank you for the question. Yeah, indeed, I also think this is really interesting. And so for the moment, what one can do, I have to be very brief. One can do a dispersion relation, okay, to relate B2 K star LL, and it's really everything is about the rescattering of charm, okay? So right now, basically, we parameterize this rescattering effect as a sum of Breit-Wigner, because the clearly dominant effect is due to the narrow J psi prime, and with that we are basically able to get this, to extrapolate the result of the thanks to the fact that LSEB give us the information about the phases, okay? So there is the amplitude analysis of LSEB that really give the phases on the different polarization. This is the crucial information. And then we can really extract these different phases and then make a precise prediction also far from the resonance peak. For a moment, we do it with a relatively simple model, which basically contains only Breit-Wigner. Also, LSEB doesn't really see evidence of more complicated rescattering, but I think we have to put it there if you really want to be precise. So this will come. And for that, it's really important, this angular distribution, full angular distribution with information about the phases.
Okay. Next question there.
Thank you for the talk, Gino.
Sorry, I discussed your measurement, which I think is beautiful.
I have a question. If you go to your next to last slide, you show the TeV reach of new contact interaction.
Yeah.
But I had understood from one of your first slides that we should not count too much on this because these assume natural order 1 couplings. So which is which?
No, thank you for the question. That's a very good question. So indeed, I hear too much information in too short time. So in this case, I'm looking, first of all, to a specific class, which are only third generation process, okay? So there, I think coupling of order 1, it's okay for pure third generation coupling. On the other hand, you see here I put Q3. What is Q3? Q3 can be a mixture, and we know that there is a CKM mix in between. So we don't know what is the third generation in general, okay? It can be the B or the top, okay? It will be something in between. So here, I put coupling of order 1 only for third generation, and then I use the CKM matrix. So when I have 3, 2, I put the CKM mixing. Okay, so there are that is the rationale here of this construction. And you see here the bounds are typically around 1 TeV. Here you get a much stronger bound, because if there is up alignment, then you really hit B-bar mixing. But on the other hand, if you go to down alignment, you don't have it. So clearly, for instance, the flavor bound can be here or can be here, and we don't know. Okay? This is why it's important to do both things. And in the future, both of them will improve, and in some cases, we really can go better than the electroweak. So indeed, it's an illustration, but that was the rationale, to have order 1 coupling, but only for third generation.
Thank you, Gino. We need now to go on. I'm very, very happy to invite Carla Goebel, who will now show us flavor physics from the experimental perspective. Thank you, Carla.
Hello. So it's a pleasure to be here and to show you some of the intriguing latest results on quark flavor physics whenever it's ready, which this is not me. It's the morning session. You are in the afternoon session. Yes, this one. I want the extra minute. Okay, so let's start. So I'm going to show some highlights of these great experiments on quark flavor physics. I had the opportunity to have Gino before me, so you already know that Higgs is the culprit here, so giving mass to all of the quarks. That means that the flavor eigenstates are not at the same as the mass eigenstates. So this gives us this matrix, which is the CKM matrix, that being 3 generations we have, and being unitary, we have 3 real parameters and 1 phase, and this single phase is responsible for CP violation in the standard model. So nature, the realization of nature for us is that this matrix is almost diagonal, which means that transitions preferably occur within the same generation, but it's also almost real with the phase-carrying elements being the smallest ones. So the unitarity brings us many relations. The most famous one is this one that brings us to the unitary triangle. And what we need to do is to make many measurements to really stress the CKM paradigm and test its internal consistency. And this is what gives rise to what we have now, that all independent measurements are converging to a single point, which is the apex of this triangle. But this is not all that is required from us. We also want to look ahead to test for new effects that may lead us to signs of new physics, and this is made through the study of rare and forbidden decays in the standard model. So let's start from the basic one, which is beta. So beta is, we can assess it through a mix-induced CP violation, and this is what we call the golden mode, the B2J psyche short, and the CP asymmetry as a function of time gives its amplitude is a direct measurement of sine to beta, and this is how CP violation was discovered 25 years ago from Babar and Bell, and since then we had precision measurements. The one that is most precise is from LHCb in 2023. But the new guest to this party is CMS that just released a result of sine to beta. They would able to do that based on AI flavor taggers. So you can see this beautiful result with a very good precision that in fact is already let's say comparable or go in the right direction to precision. So I also want to really flash very quickly this another guest to the party is a rare decay, but we just released this result that shows the potential of using a rare decay to also assess, so in the absence of CP violation of new physics, this is also a measurement of sine to beta. And you can kind of see this effect there. So let's move to gamma. So gamma, before LHCb, gamma was not really doing a good job in constraining this point. But then, and it's only the only angle that is accessible through direct CP violation in the interference of 3-level decay modes. And LHCb, in fact, this is theoretically clean, but from the experimental side, we need to really do many measurements to reach to a good precision, and this is what LHCb has done in the past, and this is the latest combination that LHCb has from last year, and allows this plot from going to this band here to this. Let's move then to alpha. Oh, no, I'm still on gamma. So this channel here is one of the good ones to make this measurement. I'm going to flash two results on this. This is from the first result we have from run 3 data in LHCb. That means using the upgraded detector. And the idea of this measurement, as I said, is a direct CP violation. So gamma can be assessed through the interference of these two paths. But we also need, as direct CP violation, we need a difference in strong phases. And this is given by the phase space of this decay. And we have to have these measurements, it's external measurements that come from Clio and now from BESS to put as inputs to really extract the CP observables and then to get gamma. So the novelty here from run 2 and run 1 data is that we are using the same method, but now a joint analysis with BESS and LHCb. So instead of using the binnings of this phase, what we do is a joint fit where BESS still provides the sensitivity to these strong phases and LHCb to the CP observables, and this leads us to the best single measurement of gamma with 5 degrees. Altogether, the precision of gamma with the latest results is about 2.2 degrees, and this is an impressive achievement. Because now I'm moving to alpha, what we see is that although gamma has had impressive results in the latest years, because it was the years of LHCb, alpha improved just a factor of 1.5. And alpha needs, in fact, because of penguin pollutions, it's necessary to do a number of isospin-related measurements, and to do that we need neutrals, and to do that we need BEL2. So BEL2 is unique not only because of this clean environment, but also because the excellent neutral particle reconstruction. So I'm showing two results. This is from last year of B0 to rho plus, rho minus, where you can, where they obtain these values, and from these values they combine with the other available measurements to give a result of alpha with a precision of less than 5 degrees. Then you see already this result many times in this conference, but this is really big news because this is a really challenge measurements and very important for alpha, and BEL2 just provided these measurements with a new technique and allowed this measurement, and this measurement alone was sufficient to resolve from a 8 to 6-fold ambiguity, and this is the new average result that Marcella just presented to us this week. So I want also to mention quickly about phi s. So phi s is, let's say, the analogous of beta, but for the B sub S system. And just really quickly showing you that although this is very well constrained from CKM fits, and CMS has this result, which it was the first evidence of a non-zero value. LHCb in his combined results still has the most precise measurements. So enough about angles. Let's go up on side. So the angles themselves already constrain the apex very well, the sides not so well. And the problem is this VUB over VCB, and you know that there is this persistent tension among exclusive and inclusive measurements for VCB. It used to be that also for VUB, but this is mild now. So this long-standing puzzle is what, so we need new measurements on that. BEL2 is giving important contributions both on exclusive and inclusive measurements for VCB and VUB. I'm just flashing two of them. And the big news, with much less precision, is that now we have on-shell determinations of VCB coming from Atlas that released this measurement in March, and also in this conference, CMS. You see that the uncertainties are still high, and also the systematics, but we are on a good way. And also, I won't have time to mention that, but I want to stress the beautiful work that Bess is doing in providing VCS and VCD. So I want to talk about this very quickly, but gamma is making its consequences in many decays of Bs, in particular in hadronic decays, where you do see like visually strong patterns of CP violation. We have this new result here. I won't get into the details. There are 3 papers on the way. But we see several sources of CP violation in vector, tensor, even in spin 3, and also SP interference. And this is one kind of consequence of this, is that we saw CP violation breaking for baryons. We are baryonic people, so this is good to see. The signal, it's just 2.5%, but it was observation. Nonetheless, we still have to search that for many other channels. We are in the path to that, but this is the only place for now. And what about other systems? So for light baryons, Bell and also Bess released the results on charm and strange baryons, but no CP violation. It's okay because it should be very small. And on charm mesons, this is one new result from LHCb, reaching a precision of that little with no CP violation indication for now for this channel, which is a Capebo suppressed channel. And also Bell has this search, and this is new for ICHEP on all this. So we are in the good path to maybe CP violation in charge. Charm is around the corner, so let's wait a little bit. So this is it for the CKM part. Let's move to the new physics searches. So Gino made a good entrance for me, so I don't have to explain to this very much. But just want to stress that really flavor physics is a magnifier to search for new physics effects. So I want to show you just quickly, this was already discussed here many times, that we have this persistent tension. I want to show those results on the B sub C to J psi tau over nu. This is good because it's another environment, and CMS has this result for this year. This is a combination of muonic and tauonic decays, and LHCb just released this result here with only muonic, I mean tau to muon. And you can compare here, it's better to see in this plot that you know already showed too, that there is a tension, let's say, of 2.4 sigma in the same direction as the RD star. So now let's move to these families that were also very much discussed by Gino, so I don't have to enter on this very much. Just want to stress that because of the hadronic uncertainties that we have and we are still trying to figure out from the theory side, lepton flavor university tests are usually more robust because you have a cancellation. And branching fractions are the least robust in terms of predictions, and angular observables and CP violating are somewhere in the middle. So this result was shown already, so this is a comprehensive analysis from the end of last year, but when you do angular analysis, you have many observables, and this is the P5 prime. You don't need to understand that more than it's an angular observable that also has these persistent tensions with standard model predictions. So this is the result that we got, and just showing here, so the tensions are at this level right now, and I'm just showing here the CMS results, which are consistent with the LHCb results. So this pattern we can also see in different ways. So instead of doing a binned analysis, we can do an unbinned and model-independent analysis to the same data to see if these patterns are there and how they are there. And really what we see is these points here are the binned analysis superimposed by the unbinned analysis. So with the unbinned analysis, we show tensions that can go to 4.3 to 4.8 sigma, and you can also see here in this plot of C10 against C9. There are many other places where I'm not going to follow this altogether, but we have, so in LHCb there are many. This is only 3 now, but you have in the local CP violation of local and non-local amplitudes, we have also this tension. If we go to B plus to K mu mu, which is simpler than the K star, there is a C9 that it's also compatible to the other measurements. First angular analysis of B plus to pi mu mu, and you have this result here of the backward for the symmetry for the low Q star bins that is compatible to the standard model at the 99% confidence level, which is also consistent with what we are seeing here. And this is a new result for ICHEP, still doesn't have too much of a sensitivity, but it's the first angular analysis for lambda B, which is sensitive to different angular observables, and it's consistent with the standard model, but is another way to look at this. What was also new for this conference was the simultaneous measurement of the differential branching ratios for 6 of these rare decays, so all these families here from CMS. And you can see that they all lie in the, this is also a persistent thing, but this is branching ratio. Remember that branching ratio are not as robust as lepton flavor violation information, but you can see that all lie down in the standard matter predictions, and I show this one, which is also very persistent and it's more pronounced. And in black are the new CMS results, but it's also shown in red the LHCb results. So let's go to another thing that Gino also mentioned, because the problem here in all these measurements is the uncertainties, for instance, coming from charm loops and resonances. But if you, instead of having the photon, you have the Z going to neutrinos, you don't have this problem. So these are very robust probes to search for new physics. Bell did that. Bell 2 did that and had this result of first evidence for B plus to K nu a while ago and just provided a new interpretation. So it seems a little larger than the standard model. So it's good to search. So this was an exclusive search. They now gave this inclusive search, which is just an upper limit. And also, just want to stress, as Gino, the what I call the little sister, because this is a beautiful result that was released in 2024, the first observation of this decay. They just have this result updated for the full data, and this is the smallest branching ratio ever measurement at the 10 to the minus 10. So we are awaiting for COTO. So COTO has, which aims to the measurement of the neutral one, which is currently at this level. They're still missing the data for the 2023-4, but this won't go to, so I forgot to say that this is in agreement with the standard model, for good or for bad, but the branching ratio for the neutral one is down to 10 to the minus 11, so we really need COTO to reach the branching ratio unless we find new physics. So I just want to highlight these other two results from CMS that on light meson rare decays, they are very different, but they are both beautiful. So K short to mu plus, mu minus. LHCb has the most stringent limit, but it's good to see that CMS is in this game too. It's compatible, let's say. And also this result here of the first observation of the anomalous decay of the eta to pi pi mu mu. They also measured before eta to mu mu, and they do this. So this is the standard model prediction. This is what they find. It's a little higher, and the peak is still very humble, but it's there. So, and this kind of result on light meson physics is interesting because not only tests low energy QCD, but it's also a portal to non-physics mediators like ALPS and axions, DEC photons. Anyway, so I think I said everything that I wanted to say. So I think that you could see that the CKM picture overall is behaving way too well, and everything put in place together with unprecedented precision. There are some places where we hope to crack the standard model, and the rare decays are still the most interesting in the intriguing place, with several observables there to be tested. The lepton flavor universality observables still deserve close attention. And what I think it's good to see is that this many experiments on the various sectors, not only flavor physics, so B physics, charm physics, strange physics, only on the quark sector, that are expanding their coverage to test, stress, and look for new physics. So flavor physics remains wide open with its most sensitive areas still ahead. So I hope that we are all enjoying all the flavors that nature are giving to us.
Thank you, Carla, for the very nice results. We have time for a couple of questions. Do I see any comments or questions? No? Okay, here.
Thank you very much for the very nice talk. You talked a lot about the BS Mu Mu results. What are the prospects for BS Tau Tau?
Two?
Tau Tau.
Tau Tau. I can't say right now. We are doing things in Tau Tau, but I can't say the prospect. Maybe Vava can comment on that.
Yeah.
So Vava is our new physics coordinator that just started here in ICHEP.
Yeah,
So.
No, thanks, Carla. And by the way, wonderful talk. I loved it. No, so we have direct searches for this ongoing, but also looking for the effect of the tails of the Tau Tau distribution in the Mu Mu analyses, and you know, stay tuned.
Thank you, Vava. One more question? Oh, yes. There.
Hi, thank you for the talk. Maybe I missed something. You mentioned in this K plus to pi plus nu nu that you would also measure the neutral case. So it would be like
Here?
Yes, I think yes.
So say again. I mentioned what?
The neutral mode. You said,
Oh, this one.
Right. How do you measure that? It's like you have a pi zero, so you have two photons, so you have to construct the pi zero and...
I'm not Koto, but I believe that that's what they do. I don't know if there was someone from Koto here, but I mean, I look at this and I ask myself the same question because it's kind of a nothing final state, but you do have the photons here, so.
Yeah, okay, thank you.
Okay, let's thank Carla again.
Hello, everyone. I'd like to introduce Professor Tsumoto Nibi from KEC with his presentation concerning charged lepton flavor and the end experiments. Welcome.
Okay, thank you very much. So I'd like to talk about the charged lepton flavor and EDM experiments. Okay, so let's start. I think one of the biggest news in this topic is 2026 Breakthrough Prize in Fundamental Physics was given to the mu1G-2 experiments at CERN, Brookhaven National Laboratory, and FEMLAB. So it's really a big congratulations to those three experiments. Okay, and then another news is that the final report from the FEMLAB G-2 was just released to the archive a month ago. The plot I quoted here is one of the, shows the beauty of what the beauty of the experiment is. In the horizontal axis, the magnetic field strength, a little bit of change. Vertical axis is the G-2 spin precession frequency. So it nicely aligned to the line, so that gives us the extra additional confidence of the result what the familiar G-2 gave us. Okay, so a little bit of a history of mu1 G-2 experiments. It starts from the CERN G-2 experiment, which was not shown in this plot. It's 7,300 parts per billion. So after that, the Brookhaven experiment uses the singleton superconducting storage magnet, enable them to improve this precision down to the 540 ppb. And after that, the Femira took over and released 3 series of the results. And last year, the final result was released with the precision of 127 parts per billion. So it's really remarkable that 50-fold improvements in 50 years. So now the world average is very, very small uncertainty. So I'd like to stress that, okay, so maybe new era of 50 years of another folds of improvement, which we start from the JPAC with the anticipated precision better than 100 ppb to surpass the familiar precision. So I think many of you know the theoretical status of the mu1 G-2, the standard model predictions. So there has been tensions between the E plus E minus driven calculation versus the very recent development of lattice QCD calculation on hadronic vacuum polarization, which will be largely discussed by the next speaker. So those two approaches does not agree each other. In coming years, the lattice QCD will continue until the experimental precision is matched. So at the moment, the experimental precision of, so for example, the white paper 2025 is much larger than the world average of experimental value. So the idea is the lattice QCD has the potential to have even better precision than now. And further scrutiny of E plus minus data and vacuum polarization from tau decays, those are the attempts, continues. And there's a new approach, the mu1E, the muon electron scattering to extract the vacuum polarization. So just by accident, there's an ongoing workshop in Connecticut, mainly discussing on this topic. There's an extensive discussion this week going on. Okay, so just a few words about the mu1E. This is a hadronic vacuum polarization from a space-like domain. This is the single measurement of leading order hadronic vacuum polarization term in the space-like domain via elastic mu-E to mu-E scattering. So through this master equation, one can convert this hadronic correction to the running alpha to the vacuum polarization contribution. So the mu1E has 2 phases. The first phase, the data taking was completed. They have a beautiful result already. From this data, they plan to demonstrate the validity of their proof of principle. Then the second phase will follow from 2030. Okay, so what about the mu1 G-2 and EDM measurements? So I would like to start from our approach at JPAC. This is to measure the mu1 G-2 and EDM simultaneously with a precision of less than 100 ppb for mu1 G-2 and 1.5 to 10 to the minus 21st E centimeter for EDM. So this experiment relies on the novel technology of cooling the mu1, which allows us to use the conventional acceleration technology. And then in the end, we have a compact storage ring. So there are features that we are going to use a low emittance muon beam, 1,000 times smaller beam emittance for X and Y, each directions. No strong focusing, 1,000 times weaker focusing, and good thing ejection efficiency. So in the end, we are able to store the mu1 in a compact storage ring, which is 20 times smaller than the familiar G-2 ring. Okay, so one of the key features of this experiment is the muon acceleration. So right now we are working on the implementation of first ever muon LINAC. So there are several sequences. We start from the conventional muon beam, 4 MeV kinetic energy. Then we stop those muon to cool them down to the 30 milli-electron volt. So there the beam emittance becomes 1,000 smaller. Then after that, we are able to use the conventional RF acceleration cavity to accelerate further. So in 2025, we reported the first stage of acceleration. And this year, we did a trial to accelerate to the 0.3 MeV using the setup shown in the picture below. So here's a brand new result we just took last June. The horizontal axis is the time of flight. And the vertical axis is the intensity at the end of the apparatus. And you see the very distinct peak. This is attributed to the accelerated mu1. So with this, we demonstrated acceleration of positive mu1 to 0.3 MeV with about 200 times intensity than our previous attempt. So coming up is a 4 MeV acceleration in 2027 to 2028, then following this final energy to about 200 to 500 MeV kinetic energy. Okay. So switching the gear to the mu1 EDM, there's a significant effort going on at PSI dedicated to measure the search for mu1 EDM. It consists of 2 phases. The phase 1 uses the surface mu1 beam with a smaller storage ring. The phase 1 will demonstrate their principle of a frozen spin technique with the sensitivity shown below. And in the phase 2 will give us the ultimate sensitivity and given the less than the 6 times 10 to the 23rd E centimeter. Okay. So this is the picture of experimental apparatus. So the apparatus is basically ready for data taking for phase 1. And people are very lively working on this experiment to start. Okay, so this is, I think, enough about the mu1 and switching the gear to the electron. So there are many EDM experiments around the world. And I think I would like to introduce one of the 2 leading experiments which provided the best limit for electron EDM. The one is using the molecular ion, JIRA EEDM collaboration. So they have announced their first result of hafnium fluoride ion in 2023. Then now they are working on the thorium fluoride ion to have about 10 times better sensitivity. This thorium fluoride ion has an advantage of being a ground state. Therefore, expected coherence time is an order of magnitude longer. So they're expecting the result sometime maybe in 2 years or so. So another the experiment is the ACME experiment. They are using a neutral molecule, sodium oxide. They have already released 2 results in the past. The ACME-3, the 3rd generation experiment, is ongoing. So here on the bottom, they have already demonstrated the 2 hours to surpass the JIRA 2020 3rd result. So lots of improvement has been implemented to surpass the previous JIRA result. So we should, we can expect the good results from those experiments in the future. Okay, and then switching to the hadronic EDM, the neutron and nucleus EDM. The neutron EDM, there's the new limit. This is the first direct limit on the neutron EDM has been given from JEDI collaboration at COSI. So this attempt is the first demonstration of the EDM searches for the stable charge hadron in the storage rings. So this technique could be used for the future EDM searches in the storage rings. So along the same line, but radioactive version of this is for example, the lithium-8 have a beta decay, the parity violating beta decays, which has a strong correlation to the spin. There's a proposal to measure this light radioactive nuclear EDM in a compact storage ring. Then going to the heavy nuclei, there is a very interesting features. Heavier nuclei, some of the nuclei is very much deformed. For example, the radium, protoactinium, and so forth. So those nuclei have a very enhanced sensitivity to the nuclear EDM due to the nuclear deformation. So at the moment, there are big competition in EDM molecule engineering. So there are, I think, new trends in EDM research in coming decades. So finally, the neutron EDM experiment, there are 5 neutron EDM experiments around the world, N2 EDM, PSI, PAN EDM, Toucan, and Beam EDM, right? But I don't have time to explore this in this presentation. Okay, so then changing the topic to the charge electron flavor violation. So this is here the view graph of charge electron flavor variation of mu1, the mu2 E gamma, mu2 3E, the mu2 E conversion. So there has been lots of effort in the past and also in the future to improve the sensitivity. So I would like to overview the status of those experiments. So let's start from the mu2 E gamma. As was presented in the Gino's talk, MEG2 has been taking data at full speed. They have already announced the result from 2021 and 22 data to surpass the MEG sensitivity. Now, the data analysis is ongoing for the 2023-24 data. Now, the MEG2 experiment is in the final phase of accumulating data taking to finish up the experiment. So now, in parallel, there's a discussion beyond MEG2 having even better sensitivity on mu2 gamma by using inner silicon tracker plus timing detector for positron, a few layers of active converter plus gaseous tracker for a photon detection to improve the resolutions, which is highly correlated to the experimental sensitivity. So here's a tentative timeline up to 2030, the R&D, and 2035 for phase 1 experiment, and after that, the data taking, construction of and then data taking in the phase 2 experiment. Okay, and another charge electron fiber variation reaction is the mu2 3E decay. There's experiment mu2 3E at PSI, searching for mu2 3E at the level of 10 to the minus 16 level. So the picture here is the setup of a 2025 commissioning run, consisting of silicon scintillator tile modules, sci-fi modules, and also the central part is a vertex detector. So one of the big features of this experiment is high voltage max pixel detector. It's very thin, but still self-standing, as you can see from the picture on the right. So as I said, the commissioning run has concluded last year, and this year, 8-week beam campaign is scheduled. Is scheduled. And then the next year, they plan to have a first physics run. Okay. So one can think about the same reaction, tau to 3 mu. There has been already reports in this conference from LHCb and CMS. There has been already some new limits has been given. And another charge lepton flavor variation searches in the tau sector has been reported from the BEL2 collaboration, tau to L alpha, alpha being a new particle, and tau to L lepton eta for the electron channel, the comparable to the previous Bell result, comparable limit to the previous Bell result as given. The mu eta channel, the most significant constraint has been given. And also the tau to mu gamma searches has been done at the BEL2. At the moment, the sensitivity has not yet surpasses the Bell result, but in the coming future, we can expect better sensitivity searches to the tau to mu gamma channel as well. Okay, so finally, I would like to talk about the mutual E-conversion experiments. The one is the COMET experiment at JPAC. It consists of two phases with different sensitivity. The picture on the left is their magnet superconducting solenoid magnet complex. They have already fabricated the magnets and starts to install and testing the magnet in the area. On the right-hand side, this is their phase 1 detector setup. The cylindrical dose chamber frame and supporting frame, and also the solenoid magnet. So the timeline is can be seen in the bottom. The detector commissioning installation to the initial beginning of 2027, and then the middle of 2028 to start the data taking of phase 1. The mutual E-conversion at Femilab, mutual E experiment, there has been a very significant preparation progress has been made. The tracker calorimeter charged cosmic ray veto are installed, and they have already started the cosmic ray test. As you can see from the picture on the right and the center, this is a detector, and on the right is the magnet there, the transportation magnet. And AC dipole has been installed and ready to commission, and resonant extraction was already demonstrated last fiscal year. So coming up is the commissioning of solenoid, cosmic ray runs, and extinction test. This is to have a very clean beam. So this experiment requires no beam in between bunches to the level of 10 to the minus 10. Okay, so the timeline is shown below. The detector solenoid ready July last month, and then coming about a year to power cool, connect power, and then they are looking for opportunity to take data a 3 months beam window for 2027 before the long shutdown. So their sensitivity plot is something like this. The 10 times better sensitivity than the Syndrome 2 experiment for 1 month's run. Okay, so I'd like to summarize my talk. So I think I tried to convince there has been significant progress on this topic since last year. mu1G minus 2, we are making transition from Femilab to JPAC with the first ever muon LINAC. Success in acceleration of positive muons to 0.3 MeV. Consolidation effort on the standard model prediction, the muoni phase 1 data in hand. EDM, muon EDM, electron EDM with molecules, and deuterium limit set by the July experiment. Lastly, I introduced the charged lepton flavor variation progress, MEG2 in the final data taking phase, with a plan beyond MEG2. mu3E concluded its commissioning run last year. The new limits are given on tau charged lepton flavor variation. Comets and mu2E are getting ready for the initial phase of the data taking. Thank you very much.
Open to questions or comments. please.
Yes, thanks for the talk. Could you go back to number 7? Go back to slide 7. This one, yes. It seems that you're going to be below 100 ppb. What is it that you are doing that makes it possible for you to beat the previous effort?
Okay, thank you for the question. So first, we have those features allowing us to have a better control of systematics. Then another reason for to have better sensitivity is to have a stronger magnetic field so that muon spin can precess faster. So that gives us better sensitivity, better statistical sensitivity in the experiment.
So, more questions?
Yeah, so regarding this slide, could you comment on the actual relevance of another J-2 measurement in J-Park? I mean, I understand this is a very nice alternative setup which advances muon, acceleration, etc. But, I have the impression that the ball is now in the theory court. We already have 2, 3, 4 independent results which are very consistent. I mean, whichever result J-Park will get, how that would change the picture, can you comment on that?
Right. So I think that's a very important point. So the reason why we still want to continue this effort is that those, the Brookhaven, CERN Brookhaven formula, this relies on the same experimental principle, and the scale of the experiment is roughly the same. And therefore, of course, those are beautiful experiments, but nevertheless, within the precision norm, we are talking about 100 ppb precision. So it's always important to double check with as different or no method as possible. And also, I hope the theory situation will improve in coming years thanks to this huge lattice QCD effort. So by the time the lattice QCD predicts much better than now, then the ball will come back to the experimental side. So having another experiment with better precision will certainly give us another opportunity to discuss the new physics.
Hi.
One more question?
Question on page 8, please. So the transverse cooling that you got here, 3 orders of magnitude is quite impressive. I mean, mice had something like 10%. This is 3 orders of magnitude. So this is the kind of level needed for something like a muon collider. But my question is, this is probably a very low efficiency process. So whereas mice is high efficiency, small emittance, here you have really good emittance, and I guess very, 10 to the minus 4, I don't know, efficiency. Do you have a feeling about what that efficiency is and whether it's something that could be, it's something you plan on improving within the experiment, or how will that work? Thank you.
Okay, thank you. Thank you for the question. So first of all, we are not challenging the mice approach. That's a great approach, and I think it's complementary. And this is not aiming for the muon collider effort. So at the moment, our beam intensity is only 10 muon per second. But we start from the 10 to the 7 muon. So the efficiency is something like 10 to the minus 6. Very low. But we plan to improve this. This is largely due to the power of ionization laser. We know how to improve it. And our goal is to improve this 10 per second to 10 to the 5th per second. So 4 orders of magnitude improvement is anticipated.
Thank you.
Sorry, excuse me. The time is up. I propose to invite the speaker during the lunch time to discuss more details. Please, thank the speaker again. The next speaker is Anders Nofield from Fermilab. His presentation concerning theoretical development in non-perturbative QCD.
Well, while the slides are coming up, I'd like to thank the organizers for inviting me to give this talk. All my life, I wanted to go to the beach in Brazil and give a talk at ICHEP, and by lunchtime, I will have accomplished both. So my title says non-perturbative QCD. The scope of that is, of course, enormous. A friend on the IAC allowed me to focus on my specialty, which is lattice QCD. But even so, that's an enormous subject. There was a conference last week. I was actually there gathering results in preparation for this talk. 40% the size of this conference. Lots of topics that may interest you, and there are links to the parallel sessions talking about those things. Here is everybody. I'm there in the middle with the yellow circle. So even so, there are many things that I know interest large fractions of this audience that I cannot talk about. And again, you can look at the latest status presented for a lattice gauge theory audience, not an audience of experimental physicists, but that's as good as you can do. I think also there hasn't been a talk on lattice QCD in many ICHEPs. The most recent one was Ying Chen. He talked about hadron spectroscopy. I will not talk about that at all. I think some of you don't know exactly what we do, so I'm going to spend a couple slides trying to explain that. We start with the QCD Lagrangian. We don't start with a model, we start with the QCD Lagrangian that has some number of parameters, one for each quark mass and then two others. The one that's CP violating we set to 0 because that's so small. And because of confinement, you can't set these directly. You have to use calculations from this Lagrangian of hadron masses in order to tune the parameters. So we use meson masses to eliminate the bare coupling via dimensional transmutation. It's very popular to use things called W0 or T0. They are easy to calculate precisely. You don't need to know what they are. In the end, we figure out what they are in physical units using m omega, or something like that, the omega baryon mass. And the key to the lattice, it's the space-time lattice, and Ken Wilson figured out in 1974 how to make this gauge invariant, so you never have to worry about breaking SU3 gauge symmetry. Then everything's expressed by an integral. You can integrate out the quarks by hand. And then with the lattice, the number of degrees of freedom is countable. If the lattice is finite, the number of degrees of freedom is finite. You can put it on a computer. And then you carry out the integrals using Monte Carlo with importance sampling. This is often called simulation, but simulation has many, many meanings. And so I think if you want to boil it down to exactly what we do, it's Monte Carlo with importance sampling using the algorithm referenced here, which is used in many fields by now, actually. And so then the basic quantity is a correlation function. You do something here, you do something there, and you study how the separation of the two in Euclidean time varies. The two-point function gives you masses, some simple matrix elements. A three-point function gives you something like a semi-leptonic form factor. You saw in several experimental talks references to semi-leptonic form factors calculated with lattice QCD. So at this stage, you then have computer-generated data with a little bit of analysis in a 10-dimensional slab. You can make some other choices to increase or decrease the dimension, but you better have a good formalism for extrapolating to the physical point, which is all the way over here. And that formalism is effective field theory. So I like to joke sometimes that at this stage, any well-trained theorist can do what we do because it's just analyzing data with effective field theory formulae. So here's a list of the EFTs. Here's a nice picture of an EFT. I just want to say on this slide that the paradigm is only done once you've taken the continuum limit and you've set the light quark masses equal to, say, the average of up and down. If you're really precise, then you need to have the up-down mass splitting as well. And so obviously simpler things finish sooner, and just because an exploratory calculation of some difficult quantity has not completed the paradigm, that doesn't mean the paradigm is a failure, it just means that the paradigm is strenuous. A recent thing we do that is in many of the things I'll talk about, and I won't bring it up explicitly, is to come up with a firmer way of deciding how to ask questions like, how many terms in the EFT should I include? Which version of it? What do you do when someone makes a suggestion of analyzing the data a different way? And particularly in the work of Ethan Neal and students and former students, is derived from Bayes' theorem, a way of understanding this and combining all of the different models. So that's a different choice of how to do the analysis into one form. And here's an example from a paper where this W0 thing I told you not to worry about is computed in units of the omega mass, and that's how we figure out what W0 is. Then other people can do their calculation in W0 units. This has a long history. The first calculation with SU3 gauge theory, but no quarks, was done in 1980. That's the year I entered graduate school. And then there was a long slog neglecting quarks, which we don't want to talk about anymore. And it was in 2003 that a paper that I was a part of showed that it actually works when you put in 2 light quarks, 1 strange quark, and calculate a bunch of things, and you find that they agree very well within the statistical uncertainties. Then we had things like predictions. I think if you had invited me back in 20 years ago, I could have given a really spectacular talk. You'll have to put up what you get with what you get this year. And then there were various other things. And again, I'm not going to go over it all. It intrigued me that it was about 23 years from Kreutz's paper to showing that we can actually get the right answer. And it's slightly more than 23 years from that paper to this talk. The human beings often get left out of this subject, so here are some of the heroes of the papers that I listed on this slide. So you've survived my introduction. I have 4 things that I think interest experimental high-energy physicists: quark flavor physics, neutrino interactions, the strong coupling alpha S, and what was mentioned in the previous talk, mu on G minus 2. Okay, so this is arguably the area in which lattice QCD has made the biggest impact on phenomenology in an experiment. There is a large group of people called the Flavour lattice averaging group, and they curate averages. And so that is a good thing to do, is to use those results, because experts have examined, are there enough lattice spacings? If there's an extrapolation to light quark masses, has it been done reliably? So use it, but they have a warning on their webpage that if you cite one of their plots, you have to cite all the underlying papers. Nobody does that, but you earn the wrath of the editorial board of this group if you don't do that. So many of the things relevant to this topic are actually several years old, and there are lots of things in progress, and I'm only going to subject you to 2 of them. You can see lots more in the talk by my namesake, Andreas Juttner, at the Lattice Conference. And the 2 that I want to talk about focus on this long-standing tension between exclusive determinations of VUB and VCB. These are given by these colored bands. I think focus on the narrower ones. And here's the average from there, compared to the determinations of the same quantities using inclusive decays. And nobody has a good idea what's going on here, except maybe someone made a bit of a boo-boo somewhere. So we have work on the exclusive decays. I have some technical information at the top that I won't go over. But the 2 key points is that from the previous calculations that are 5 and 11 years old by now, we have ways of removing the dominant uncertainties. And it's based on things that we've been working on for quite some time. So here are some raw data. There are 3 calculations for 2 independent form factors being carried out by Nick Kasser, a graduate student at Colorado State. And okay, this looks like a mess. And I would like to make 2 points. You have many lattice spacings here. The lattice spacing dependence is not very big. You have several different pion masses. That means the same as light quark masses. We use the variation to make sure that we get the right answer. Oh God, 10 minutes. And most of the vertical spread is because the heavy quark mass varies on this plot. They have something similar for B to D, which gives you VCB. And here you see some fit functions overlaid on these data. And as a preliminary step, we then take the result of this extrapolation, extrapolate over the full kinematic range constrained by analyticity and unitarity, and you see that we have, we'll have a nice result where the uncertainty is dominated by the statistical uncertainty. A big new thing, in my opinion, is you can now do lattice QCD for inclusive processes. So all the details were covered in a talk by Shoji Hashimoto. And there's a new paper on BS to inclusive final states with a strange spectator and a charm decay particle. And here are some of the authors of those papers. So this is what they get for the rate. They have 3 lattice spacings. All of the lattice spacings have physical light quark mass, so that's good. And so what you really want to do is find out, what do these guys say? Do they agree with the inclusive? Do they agree with the exclusive? Or do they agree with the inclusive? Well, unfortunately, the errors, not least the experimental error from BS decay, is too large to weigh in. So we're really excited waiting for them to do the inclusive B decay rather than B sub S. Okay, neutrinos. Neutrino physicists need nuclear models to do their energy reconstruction, and the nuclear models have many moving parts with hadronic physics and nuclear physics moving this way. Lattice QCD can calculate most of the hadronic things that you need, although there's only one that is mature at this stage, but it's a very important one, the axial form factor of the nucleon. So there are 5 papers with continuum limit physical quark masses that are on the market. And Aaron Meyer has averaged these and at the same time incorporating constraints from how the large Q-squared behavior has to fall off. So here is a version of Aaron's work that he gave me. This black thing is what's in generators now. It's from older work by Aaron Meyer and others using deuterium. And what you see is that all the lattice calculations lie above that. They agree with each other in the region where they actually have data. And then you have this extrapolation. So you see the lattice uncertainties ballooning as you extend beyond the range of data. That makes sense. And then you see this very narrow thing down the middle. And that's because the constraints have taken over. This is maybe a little bit adventurous because the data are being applied in a region where the originators didn't exactly think it would go. And so I'm not saying this is the final answer on the uncertainty, but it's something interesting to think about. And it shows that there's progress being done. And this is important to neutrino physics because if you look at the quasi-elastic peak, which is used to normalize all the generators, it makes a significant difference whether you use the defaults that are being used now or these new results from lattice QCD. Another important thing of the past year is a new determination of the strong coupling alpha S. This, of course, influences everything at the LHC. Here is a summary plot. You see that the lattice, previous lattice average and the PDG average from other processes agree. So that's nice. A group called the Alpha Collaboration has combined the two on the previous plot that had the smallest uncertainties, the so-called step scaling and decoupling. And here what they do is they trace out an observable that's proportional to alpha. So this is a calculation of the non-perturbative running with a controlled step here all the way until it matches to perturbation theory. And so then in their scheme with the weird name Schrödinger functional, they get the lambda parameter, and then there's exact one-loop conversion to lambda ms bar, and then you can run back and get alpha. This paper is in Nature. This is their chart to make it easy for the biologists who read Nature to understand what they've done. So here's some numbers. You can read the numbers yourself. The key thing is that this is a bar chart of the of the uncertainty budget, and the purple ones, you need to add them up. They dominate. All of the other alpha S determinations 2 plots ago were dominated by systematics. So where does it land? It lands basically in the middle of what you had before. Okay, U on G minus 2 in 4 minutes. So here's a table of all the contributions. Of course, QED is the largest, and I'm going to talk about why the total error is larger than the discrepancy we now have. You see that it comes from theory and not experiment. You see that it comes from HVP, which stands for hadronic vacuum polarization. Congratulations to the experimentalists on their breakthrough prize, by the way. So there are 3 methods to do this. You know, you learn in your quantum field theory course how to do this diagram, and that's how you get this K sub E of omega squared. That's the black part in this diagram. And then you need this polarization function. Have this polarization function at space-like separation is something that U on E is going to do. So Benazzoni at ICHEP 2036 will tell you all about that. What's usually done is to use dispersion theory to rewrite this in terms of a quantity that's proportional to E plus E minus goes to hadrons. You could also take a step back from here and go back to coordinate space, and you can write this as an integral over Euclidean time, which is what we use in lattice QCD. So these two are related by Fourier transformation, this by dispersion theory, and this by a Laplace transformation. You can't reverse that very easily. And so this is what the Laplace transform looks like in pictures. One side has lots of peaks, and the other is just a really smooth, boring function. Okay, so I will do a little bit that's not lattice QCD. I'll use experimental data, analyticity, and unitarity to try to estimate this quantity. You see from these pie charts that the dominant contribution comes from E plus E minus to pi plus pi minus, and also the dominant contribution to the uncertainty in using the second technique of the previous slide. So here is data from the then 2 most precise experiments, Chloe and Babar. You see about a 2.5 sigma when you add it all up, discrepancy between the two. This got mudged in all previous determinations. And then since then, an experiment at Novosibirsk, CMD3, added data, which is now the most precise, and it's another 2.5 sigma higher than Babar, and therefore 5 sigma higher than Chloe. So we have experiments that are in tension with each other, providing the key ingredient to estimating the hadronic vacuum polarization. So the mu on G minus 2 theory initiative's white paper from last year gave us this, and this is the difference between the standard model and the experiment. I think this plot is updated for the most recent measurement. So you see all the things that people used before were over here that led to the quarter-century idea that there was a signal of new physics in this channel. but CMD3 is all the way over here. And meanwhile, lattice QCD has gotten much better, and so what the theory initiative now recommends is a so-called consolidated lattice average, which is this blue band here, and as mentioned in the previous talk, this is now less precise than the experiment, but in perfect agreement. There are people who dream that as we reduce uncertainties, we'll end up with a narrow band over here on the left, but it's just as likely that we end up here, so I don't dream that way. Okay, I'm out of time. The consensus here is that you cannot average those discrepant results in the E plus E minus goes to hadrons way. Instead, you use this consolidated lattice average. Okay, I'll do the lattice slide in one quick thing. We slice it up in lots of different ways for various reasons, which you don't have time to learn about. The point of this thing, and I hate it when people show slides with lots of plots they don't explain, so I'll explain it very briefly. These are 3 different quantities that are pretty difficult, but not impossible for many people to calculate. And what you see on all these plots, this one is the sum of the other 3, is that the lattice calculations agree the way they should if people are estimating their uncertainties in a sensible way. You also see that the data-driven ways disagree unless you switch off the old experiments and replace it with CMD3. Okay, there's also another hadronic contribution. There's no problem there. So there is a meeting going on this week to discuss what to do. The E plus E minus side is anticipating updated measurements from several experiments and figuring out whether the QED Monte Carlos are good enough. They talk about things you usually talk about at the LHC, like next to leading order and parton showers. And the lattice side is talking about reducing the uncertainties to measure the to match that of Fermilab E989. And here are some of the heroes of this effort, including Simon Eidelman, who passed away a few years ago. Okay, so I'm out of time, but I only have one slide left. Lattice gauge theory is a tool of broad applicability. I had to select viciously topics. I left out some I would have loved to talk about, but I chose ones that I thought are relevant to people in the audience. Many calculations are hitting 1% or less, which means that you can't just do QCD, you need to do QCD plus QED. Nucleons are harder than mesons, but the axial form factor is making progress. And I'll just stop there. Thank you for your attention.
Open to quick questions or comments.
Hi, Andreas. Thanks for the talk. Could you go to the slide with the B to DL new? It was around page 16, but...
Which slide?
It wasn't numbered. It was after page 16.
In the quark flavor section.
Yes, somewhere around, a bit further, more... Yeah, somewhere around here. I guess the question is, so this is for the pseudoscalar transitions. If you wanted to do B to D star L nu with the vector meson, I guess it's more complicated, more form factors. Is there some potential for that as well, or?
Yes. So when I went back to this slide, actually, this 2021 paper is our previous effort on B to D star. Our previous effort on B to D is even a couple years older than that. And as you say, there are 4 form factors, so it's more complicated. And for reasons of staging, what you do when on the computers, the data generation is behind this, and so therefore there's not really any analysis of that going on yet, and therefore there's nothing to show. But it will happen, and when you see this paper come out, you can expect a few years after that B to D star at comparable quality.
Okay, thank you.
Time for one more quick question or comment. If not, thank the speaker again. Close the section and go to the lunch time.